So hello everyone, this is lecture 12 for the classical physics. In the last lecture we did up to virial theorem. Okay, so today we will start with gravitation. So you all have some idea about gravitation because you are studying it from very elementary classes. So gravitation is also a part of central force because we know this is an example of central force. So let's see, we'll start from very basics. So what was Newton's law of gravitation? So if there are two masses, 1 and 2, then each and every mass will apply force on each other. Okay, and this magnitude of force will be depending on the product of that mass and inversely proportional to the distance between them. Okay, if distance is r, then force will be inversely proportional to that distance and product of these masses directly. Okay, from this we can find this formula, means the magnitude of force will be g m1 m2 divided by r square, where this g is a constant of proportionality and we call this gravitational constant, and its value is 6.67 into 10 to the power minus 11 in SI units. Okay, so remember this value, this is a constant throughout the universe. Okay, so now let's see how we call it as central force. See, the force on this object due to this we call as F21, means on 2 due to 1 is F21, is always radially inward. So if vector r is in this direction, so force will be minus fr r cap. So that's why it is an example of central force. Now, and how you can find the magnitude of force or the direction. So F on 2 due to 1 will be g m1 m2 divided by r square, and the r cap means inward, radially inward, and F12 will be equal and opposite to this F21. So they will follow this relation, and their magnitude will be this. I already told you about this magnitude. Now if it is a central force, so it will be conservative force. We already studied about conservative forces. So in conservative forces they follow this relation, del cross F is 0, and F can be written as the gradient of some potential, scalar potential. And here we have introduced, means in the conservative forces we have potential energy, and total energy is the sum of kinetic energy plus potential energy, and this is mechanical energy. Okay, and this always remain constant. This is conservative force. So this is all clear to you. So we just made the base. Now let's move forward. So let's see some statements. Every particle in the universe attract each other with a force directly proportional to the product of their masses and inversely proportional to the square of distance between them. This is our Newton's law of gravitation. Now these were our some properties, means first was this law, second was it is central force, third is its conservative force. Now for this they follow superposition principle. Okay, so what is the meaning of superposition principle? If there is this mass m and there is some these small masses m1 m2 m3, okay, then force on this mass due to this m1 and this mass due to m2 and this mass due to m3 are independent of each other. Means if it is this one is f1, this is f2, this is f3, this f1 is not affected by f2 and f3. This is separately, this force is available, this force and this force. Okay, and if we want to find the net force on this mass, this will be the vector sum of these three forces. So that will give you the net force on this mass. Okay, so this is called the superposition principle, means net force will be the sum of these individual forces, and this force is not affected by these two and any other else. Okay, so they will be independent of each other. So net force will be F1 plus F2 plus F3. Now there is this fifth property, that is gravitational field. Okay, so let's study about this. What is gravitational field? So if you want to define it, it's just like there is this mass m, okay, and there is this sphere of influence, means at any point if you place, there is no charge still there, if you place any m0 charge here, then it will feel a force towards the center. Okay, so the force due to which means by which we are feeling this force is called the gravitational field. Means when it was not there, then there was something, so that is called the gravitational field. Okay, so this sphere of influence represents the gravitational field. So let's see the statement. The sphere of influence surrounding a mass in which its gravitational effect can be observed is called gravitational field of this mass. It can be expressed in two forms. So when there was no mass, then if you place some mass, then its gravitational effect of this point can be observed, and the reason behind it is gravitational field. Okay, so it can be expressed in two forms. we will study them separately. First is vector form and second is scalar form. So when it is in vector form, we call it as gravitational field intensity represented by I, and in scalar form represented by V. So let's start with first, that is vector form. So the gravitational field intensity or strength is defined as the force experienced per unit mass acting on a test mass. So per unit mass means the force felt by a unit mass when it will be placed in a sphere of influence is called the gravitational field intensity. And we place a test mass because this test mass is nothing. So to define gravitational field, to give it a physical significance, we define that force as gravitational field, means we place this m naught here. And what is m naught? M naught is tending to 0, means there is no mass, negligibly very zero mass. So that is called the test mass. M naught will not exert any field or it will not interact with others. Due to this test charge, there will be no field and no distortion in the around it, and no field means nothing is m naught. Okay, we just place it to describe this gravitational field. So per unit mass, the force you will have is called the gravitational field, and m naught will multiply, it will give you a force. Okay, so let me give you the expression, it will be more understood to you then. So if force is this on this m naught test charge, then per unit mass, this will be our gravitational field intensity. So this is the gravitational field intensity, it is radially inward. Okay, now for any, if you place any m1 charge now in this sphere or in anywhere here, then force can be given by m1 into I, where I is the gravitational field intensity. Okay, so this is the definition. This is having you just multiply with m1, you will get the force. So that's how you define. Now there is the second thing, gravitational field intensity due to a solid or hollow sphere of mass m and radius r at an external point. So we need to find the gravitational field intensity due to a solid or hollow sphere of mass m, means this is our, so this can be solid or hollow. So we need to find the gravitational field intensity at this point. So what we will do, we will consider the whole mass concentrated at this center and just use the formula, this one, gm over r square. This will give us gravitational field intensity. So if total mass is m, then IP will be minus gm over r square. Okay, so at any point P, it will be this. So it's a simple thing. Now gravitational field intensity I will be 0 at an internal point of a spherical cell. So what if this was not outside and inside, means there is this spherical cell and cavity inside. Okay, and we take a point inside, then what will be the gravitational field intensity? It will be 0. At any point you will find it will be 0. So let's see the proof. So it is a very interesting thing. So let's say this is our origin, means this is our center of circle, and we take any point like this here. Okay, and we draw these two lines, means we take this line and we take this line. Okay, now we have divided this sphere into spherical cell into 4 parts, 1 2 3 4. Now this is a solid angle made by this area of sphere, and there is a solid angle made by this area of sphere. Okay, and the mass per unit area density, mass density of this sphere is sigma. So the arc will be made here, and this whole area above this solid angle will give you mass as sigma d area, because sigma is mass per unit area. So it will give you this mass of this area, and mass of this will be sigma dA1. Okay, and this will be same. So first let's find the gravitational field intensity at this point due to this mass. So what it will be, g mass will be sigma dA1 divided by r1 square due to this one. This distance is r1 and this distance from here to here is r2. So simple formula, gm over r square. So gm will be sigma dA1 divided by r1 square. The magnitude we are taking. Okay, so here g sigma, now this dA1 over r square, dA1 over r square will give us the solid angle d omega. So we write it as this. Now takes the gravitational field intensity at this point due to this sphere. Okay, due to this part. So it will be again g m over r square. So mass is d sigma a2 and g sigma a2 divided by this r2 distance square, and again this dA2 by r2 square will be d omega. Okay, So it will be g sigma this, and it will give you this value again. So see, these two are same. So gravitation intensity at this point due to this one and this one is same magnitude wise, but opposite in direction, because of this it will be in this direction, and because of this it will be in this direction. Okay, so the net sum will be 0, means if we take the vector addition, so I1 plus I2 will give you 0. Now see, we need to find from all the areas, so we covered these two parts. Now see these two areas, this one and this one, these are totally identical, means they are same. Okay, so due to this one, whatever this was, it will be same as due to this one, so they will cancel out each other, and total sum will be 0 again. So that's how we can say that in a spherical cell inside, their gravitational intensity will be 0. Okay, now what if for a solid sphere, means this was due to a hollow sphere, field intensity at an internal point of a solid sphere. So now radius is less than r, but this is solid sphere, so we will divide this, means this is origin, this is center, and this is the point where we need to find. So we will draw a sphere around it. Now let's consider this point not on this line, just little bit inside. Okay, so we divide this sphere into two parts, one this one and two is this one. So due to this one, this point is lying inside, so we will follow this property, and it will be 0 due to this one. So field intensity at point P due to part 1 is 0. Okay, now we will check for the second part. So this is a solid sphere, and at this point, so it will be, if say that mass of this whole sphere is m prime, so field intensity will be using this property. We can find this, it will be r minus gm prime over r square. Okay, now we need to find this gm prime to find the gravitational field intensity. So m prime, how you can find? See, the density of this whole sphere is constant. Okay, mass per unit volume is constant, so m prime over total mass, let's find that ratio. So m prime over m will be volume into density. So density is same, and volume is 4/3 pi r cube for the small one, and for the complete sphere it will be this. From here we can find the relation between m prime and m. So m prime will be this, and this m mass is known to us. Okay, so from here we will just substitute this m prime value in this equation. So we will get I2 will be this. Okay, and in place of r square, means in place of m prime, you will write this, and you will get this equation. So minus gm over r cube r cap. So this is a very important result, we will use it. So total intensity will be I1 plus I2. I1 is 0, I2 is this. So total gravitational field intensity at point P will be this. So remember this result. Now let's see on the surface point, means if there is this point and we need to find the gravitational field intensity, so it will be simple, minus gm over r square. We already discussed this. Now let's discuss this important point. Very important actually, the acceleration due to gravity, g. So see, we have this earth. Okay, and anything over this earth will going to feel this force due to earth, that is gravitational force. And not just on the earth, if it is anywhere in the surrounding, so it will gonna feel a force F due to gravity, that is gravitational force. Now we know force is nothing but mass into acceleration, so that force will give us a acceleration. Okay, and that acceleration is called the g, acceleration due to gravity. So this is mass m here, so this will gonna feel this force mg, acceleration is g, this is also gonna feel the same. Okay, and if it is point somewhere here, it will also gonna feel this force F. So this will be in the form of mg, and here g is the acceleration due to gravity. Okay, so hope it is clear to you what is. And let me define one more thing. We call this mg as weight. Okay, so whatever force we are feeling, so that is called the weight on the earth. Okay, many times you find the questions in the form of that weight is 5 Newton, 10 Newton or all. Okay, so that is the force given by the earth. So the acceleration produced by the force of gravity is called the gravitational acceleration. Let's find the value. So force is on a any mass m, small m. So force will be this due to earth. This is mass of earth, this is radius of earth. So over the surface we are finding now. So over the surface it will be r distance, and ma will be this. So m will cancel out and we will get this acceleration as minus gm over r square. So this is our acceleration due to gravity, that is g. Now there is some properties of g. G is independent of mass, shape, size, etc. of the falling body. So any body is falling on the earth, so g is independent of their mass, shape and size. It will be same for everything. And it is not a universal constant, it will vary from place to place and depends on the place, position and planet. Okay, about means these factors are varying this g, mass, radius and all. Okay, so we will discuss about the variation of g on the earth. There are 4 factors actually which contribute to the variation of g. We will discuss the all. So first is shape of our earth. So what is the shape of the earth? It is oblate. So oblate is what? Means it is bulging in some areas. Means at the equator the shape of the earth is bulged. Okay, so it's like we pressed some sphere from the upside, so we'll get this kind of structure. And because of this radius of earth at the equator will increase as compared to polar region. Okay, so r is greater than rp. It is at equator, it is at poles, and the difference between these two radius is approximately 21 kilometer. Remember these numbers, very important. Now we will see from this formula that g is inversely proportional to the r square. So smaller will be the r, greater will be the g. So at pole we have small r, so we'll get greater g at pole as compared to earth. So if someone is moving from earth equator to pole, so small g will increase. So as one moves equator to pole, he will observe the increase in g. So that's it for today. The next lecture we will study about the small g variation at some height, means when we are moving to the height, some height from the earth, or we are going in depth in the earth, or the variation in g is also due to the movement or the rotation of the earth spinning. So we'll see all these factors, okay, in the next lecture. Thank you everyone.